So hi everyone, and welcome to Distributed Tracing and Monitoring with OpenCensus. Meir Lehman, who was professor in London Imperial College, formulated a set of rules which later became known as Lehman laws. One of his rules says that change in software is inevitable, and it's not necessarily a result of bad design or bad implementation. It's just because things change over time, and as a result, we need to adjust our software, and there is nothing bad about it. So it's not surprising that in the last 20 years, we were evident to software evolution that happened and changed our lives and the technology that we use. We were running our workloads on premises, and then at some point, we started to migrate these workloads into the cloud. We run the workloads on virtual machines, but then after some time, we realized that we might optimize the footprint of our workloads to run it on containers instead of virtual machines. And then if previously we were developing applications as monoliths that were hard to scale, over time, our development teams grew up, and so now we have multiple teams working together, and so it's much better to develop microservices so that every team can focus on its own microservice and make it much more efficient for everyone. We were developing using a single stack, and nowadays you can find many applications which are microservices developed in multiple programming languages, so-called polyglots. And if previously people were using single cloud, nowadays, many companies realize that they need to use multiple clouds or multiple cloud providers and a hybrid because of some compliance constraints or for redundancy or some other reasons. Now, even the second wave of this innovation, previously people were running on virtual machines, went to containers, but now even from containers, people move towards the serverless world, which is cloud functions or other types of serverless workloads where you focus mostly on functionality and less on managing your infrastructure. So with all these changes also come new challenges. How do we debug software like this when we move pretty substantially from one product to another, from one language to multiple languages, from one infrastructure to a different set of infrastructure? How do we deal with problems? How do we detect that there is a problem with our software, and how do we fix those problems? How do we nail the development practices? Do we need to adjust the practices to the changes in the technology, or maybe we can continue working like we used to work maybe 20 years ago? How do we deploy the workloads that we develop nowadays? Do we need to package them in a different way than before? How do we manage configuration? How do we manage security and more specifically secrets that you might have in your application? So there are a lot of problems that nowadays need solutions, and obviously this talk cannot solve all of these problems, so we'll focus on one area, which is observability. So let me first introduce myself before we actually delve into this topic. So I'm Simon Zeltser, software engineer at Google, focusing on developer experience with infrastructure and operation tools. You can find me on GitHub, Twitter, LinkedIn, or any other social media. So what is observability? One easy way to describe it is being able to debug the system and gain insights into system's behavior. People say nowadays that observability is just a new way to say the older term which everyone knows as monitoring, but that is not true. Cindy Sridharan came up with this nice Venn diagram which explains why it's not true. With monitoring, typically you create your monitors that check on predictable failures. You know that you can write some code which will repeatedly check on some condition, and if that condition stops working, you know that likely you found a failure. With testing efforts, you can verify your software before you're deployed to production. With observability, it's actually all potential issues that you might find throughout the full life cycle of development, be it before you deploy to production, during the run in production, or any other combination. So every possible failure that can be detected in your systems, and being able to understand the source of that failure, this all falls into this area of observability. So observability is not only monitoring, it's way more, and please don't confuse it. Baron Schwartz, who was very known for his contributions to MySQL, once said that monitoring tells you whether the system works, and observability lets you ask why it's not working. This is another pretty good statement that helps understanding the difference between monitoring and observability. Now, when we talk about observability, we need to have holistic approach. We need to look at the same timeline and put different signals that come from our systems. It could be traces, it could be metrics, it could be profiling information, it could be logs. Putting all the signals on the same timeline and then trying to understand from the entire context what's going on with your system is a very efficient way to understand and spot the problems. Now, what if I told you that there is ultimate recipe for making your distributed systems always reliable and successful? It's 3 things that if you implement these 3 things, you are going to be successful. It just always works. So first is track system health, detect problems, that's the second thing, and then fix and refine, or like rinse and repeat. It's relatively a simple life cycle, and everybody can implement it, but apparently people still fail. And the reason people fail, it's because this problem is in a way similar to a gym problem. You know, if you want to lose weight, you can go to gym, you can practice 3 times a week, eat healthy, and the results will come over time. But still, people don't do it. And the reason they don't do it is because even though the recipe is well known, it's not that easy to implement. Observability in distributed systems is hard and expensive problem to solve. You need to deal with context propagation between different components, multiple environments, sometimes things like vendor lock-in, external dependencies, of course, high costs, and as a result, you might find it a pretty complex problem to solve. So meet OpenCensus. OpenCensus is a single distribution of libraries written in multiple programming languages that help you with metrics collection and tracing of your distributed systems. So to kind of delve a little bit more into what it provides, it's a single set of APIs implemented in 8 programming languages, including all the popular ones, for tracing and metrics collection. It is also providing integrations with popular web and remote procedure call frameworks so that you can get more visibility into how your dependencies are doing without doing any extra work because it already comes integrated. It also provides standard protocol for context propagation between different components of distributed system. We'll talk about that a little later in this presentation. Then it provides exporters, which allow you to create all these observability signals using the libraries that are all open source, and then send it to the backend of your choice. It could be application insights if you work with Azure, or it could be Stackdriver if you work with Google, or any other popular vendor for monitoring, tracing, and other observability technologies. Finally, it provides the collector that we'll talk later on about, which helps you with smart traces and metrics collection. Okay, so I'm going to show the demos in C#, and that's why I put this slide that explains the NuGet packages that you can download to use OpenCensus in C#. But similarly, you can find NPM packages for Node, or Go packages, Java, and so on. So basically, for all the popular languages, there is a corresponding repo which holds the development for these packages, and then in the relevant package manager, you can find all the OpenCensus packages. So for .NET, the 4 packages which are likely most important to you is OpenCensus.abstractions, which defines all the contracts, all the APIs that we'll talk about without the implementation. And then just the OpenCensus, which is the actual implementation for these contracts. Then if you want to instrument your HTTP client, you can work with OpenCensus.collector.dependencies. And for ASP.NET Core, you can work with OpenCensus.collector.ASP.NET Core. And then there is a full list of packages that you can access, which also includes packages for different exporters like Application Insights, Prometheus, Zipkin, Jaeger, and so on. And we'll see some of that today. So before we delve into the actual samples in C#, how you can instrument your code and do tracing with OpenCensus, let's talk about what are the typical paradigms when you instrument your code with tracing. So typically, there are 2 scenarios, like roughly speaking. One is agentless, and another is using agent. In agentless scenario, typically you have the workload up and running. It could be in container, it could be in the VM, it could be on Windows, on Linux, or any other operating system. But basically, your application runs likely in process. And then there is a component which lives in process with your application that collects all the traces that the application produces and then sends these traces to the backend of your choice. Okay, in this case, your application needs to do some work to basically call the right APIs to initialize this exporter, and then the exporter will send the traces that get generated all the way to the trace backend. It is typically the easiest and most common approach, but it will not work for all the scenarios, and this is why we have the second approach, which is using agent. With agent, typically you have your application up and running somewhere, container, VM, whatever, and then the agent lives alongside your application, but it's kind of side by side. So it's not in process. It could be like a separate process, or it could be a sidecar proxy if you run in container in Kubernetes, for example. But it's a separate component that lives in a different process, or might be even different container. In this case, application might produce traces, and these traces will get generated and sent. It could be std out, it could be other ways, but essentially the application doesn't know that there is a separate component that collects all these traces and sends over to the backend of your choice. This is very common in cloud environments and also in systems which need to scale up quickly. So in order to kind of be on the same page with all the terms for tracing, let's explore what is trace in the context of OpenCensus and what can we do with it. So first of all, trace is a collection of spans. Span is a single operation in the trace. It's like a logical operation that has the start, has the end, has its name, and everything that happens between the start and the end is what you want to kind of showcase in this span. Sampler is a component that decides whether to export a given span or not. We'll see later on that we might not always want to export all the telemetry that our systems are producing, but we might want to export only subset of all traces. And this is why we need a component that takes this decision, what to export and what to leave. Then there is exporter, which is the component that sends all the traces that were collected locally, be it in the first scenario that we discussed without agents, or be it in the second scenario. But essentially, these traces that were created, they need to be sent over to the backend of the choice, and the exporter is the component that is in charge of sending these traces to a backend. So in this graphical example, you can see that we created a trace which basically shows the flow of a system. We called messages, which made a call into auth, which made a call to cache.get, and so on. And it looks like a call stack, but the difference is that it's distributed system, so every component could live on the same machine or could also live on a completely different machine, cloud, or other environment. Okay, so now let's see how to kind of get started to create a trace using C# with OpenCensus. And again, the reason I'm showing it in C#, it just, I choose C#, but very similar APIs, identical besides the difference in the language, also exists in Java, Go, Python, and other languages. So if you use a different language, you're welcome to try similar things using that language. So first of all, we need to configure the exporter. We are going to use the first agentless approach. So our agent is we don't have it. It's basically code that we need to initialize that will send all the traces that were generated all the way to the backend in process. So I create, in this case, Zipkin trace exporter. So in my demo, I'm going to use a distributed system called Zipkin, which some of you might be familiar. It's all open source. It was invented by Twitter, and it allows you to collect traces and then visualize the flow of your distributed system. So we'll see it shortly. So typically with exporters, we have the options object where we specify details of how to connect with that specific exporter. And in this case, we also specify the name of the service for which we create all these traces. And then we provide tracing.export component, which is where all the traces get generated locally before they are sent over to the backend of the choice. And then we start the exporter. After we created the exporter, we need to configure sampler. Sampler, I remind, it's a component that decides whether to take the trace and send it or skip it. In our case, we are going to use a logic which will take every single trace. So 100% of all traces that were generated will basically take these traces and export. But you can also implement any other logics. You can take percentage of all traces, and you can take some other decision based on some statistical analysis that you do or whatever else it could be. We'll discuss that in a bit more details in a third demo. But in this case, you can see that we have samplers.alwayssample, which is the one that will take all the traces. Then if I want to get a hold of the object that produces traces, there is a way to do so with tracing.tracer. You can also plug this into inversion of control system if you use C# or something similar in Java, because all these objects, they implement corresponding interfaces. So for example, tracing.tracer implements interface called iTracer, so you can plug it really easy into your dependency injection framework. Okay, now the actual part. So before this point, we created the exporter, we created the sampler, but now we actually need to generate the traces and the spans that belong to these traces. So this is how we can do it. I typically recommend to use scoped spans, which means that you can narrow the scope of the span that you create with the using statement in C#, so you don't need to explicitly call finish for that span. But essentially, we create a span, we give it a name, we start it, and then we can do some work, and we know that everything that happens within the scope of that span is going to be accounted for in the duration of that span. Okay, so let's see it. Before we actually see it, there is a link here that has all these samples that I'm going to show. So you can later take a look and reproduce it yourself. But now let's try and see it. Okay, so basically the code that I'm going to show you is very much similar to what we saw in the slides. Okay, I'll just go really quickly. Okay, we create the exporter, and then we configure the sampler, in this case 100%. If we want to get a hold of the tracer, we can do it this way, or in any other method by tracing.tracer. And in this case, we create a scoped span for the Uber span that starts the entire activity here. For simplicity, since it's just getting started sample, I just do everything on the same machine. But we'll see also later on how things can be done on different machines. So this is the do work method that we try to instrument. And in this do work, we also have multiple iterations of something. Also, do work itself runs in multiple iterations. And every iteration, we want to create a span that basically describes the duration of that. So this is how we can do it with the start scope span. And we can also add annotations, which basically means that we can add some additional metadata that describes the span that we just produced. So for example, if you work with big data tables, you might add a notation which says what table are you working with. Could be useful when you look at the traces. So let's run it and then see what it essentially produces and why it's good for us. Okay, so it's doing some busy work. So there are some threads .sleep for simulating that things take time. It's like really simple thing. Okay, so it looks like it finished. And now I can go into Zipkin. So in this case, I run Zipkin in a container. So it runs locally on my machine. It could be Zipkin somewhere else. And I can do find traces for this service that we instrumented. And you will see here that we have 11 spans of one trace. Okay, so for this service, we created this Uber span for main. And in main, we made a few calls for do work. And every call for do work took a different duration. You can see it here by the number of seconds that every call took. And then if I click, I can even get some additional data, like in walking do work. This is the text that we added in our code. So it's a relatively easy way that helps you visualize how your system behaves in terms of which component calls which component and how long it takes. So of course, when you have microservices architecture, it's going to be really handy to see which microservice calls which microservice and what actually happens in the flow. Okay, so I'm going to start the second demo, and then we are going to start talking about it because it needs some warm-up time. Okay. So with tracing demo that we just saw, it's relatively easy to create traces, it's easy to create spans, and there is this exporter component that does all the heavy lifting of taking the traces and spans that were created on our component and sending over this information to the backend of the choice. But there are some problems that we still need to solve. One of them is trace context propagation. So you might have multiple microservices talking to each other. So in this case, front-end talks to add service, but also to checkout. And then checkout makes two calls downstream to payment and to email services. And if you think about this problem that's happening in multiple transactions in parallel, so you might have multiple users which execute exactly the same code path, exactly the same activity, and you want to distinguish between different activities of different users. So for that, you need to have trace context propagation. Another reason why it's an important problem to solve is because essentially you might use things like A/B testing. So with A/B testing, if you decide to give your control group version A and then your test group version B, might be that the components downstream that serve the users that got version B, they might behave differently because user gets version B, right? Because you try to roll out a new version, so you might want to expose a different behavior for B versus A. So for that, you need to provide some additional information for the downstream components so that they know that they need to behave differently. And this is why we need trace context propagation. This, among other things, also helps us to construct this nice picture that shows who calls who and why, that we also could see previously with Zipkin. If we have this trace ID that is propagated all the way throughout the call chain, and also all the spans have their unique ID, which is associated with corresponding parent ID, this is when we can create these graphical representations like you see on the right-hand side that help you understand really what happens with the given specific transaction, and also to distinguish that transaction from other transactions that are of similar type but were initiated by a different user. So luckily, with OpenCensus, you get this for free. OpenCensus came up with W3C standard, which was recently approved. And this standard basically defines what does it mean to propagate context between component A and component B in distributed systems. And the industry is steadily moving into this standard. So we're not going to get into too much details. There is a link here to the actual proposal on W3C. But the good thing is that all of the libraries that you can use with OpenCensus, be it for traces or metrics collection, in any language that you choose, they all implement this trace context propagation component or algorithm out of the box. So you can be sure that if you choose to use it, it's a good choice because everyone is going to align with this. Okay, so we were talking about mostly traces collection, but OpenCensus also allows you to do metrics collection. So let's talk about that. Now, just like with traces, let's first talk about the different terms that we have in this world of metrics collection with OpenCensus. And then once we nail the terms, we'll see the demo that kind of glues all these things together. So what you can see here on this picture, this is an excerpt from Stackdriver, which is a Google Cloud system for application performance monitoring. And this is just some random graph. And on this graph, we'll see different terms of OpenCensus and how they play together. So first thing is a measure. Measure is what you actually want to measure and what are the units for that. So CPU utilization is example of what we try to measure in this specific case. And there are no really units because it's typically percentage. Now, second term is tag. Tag is additional metadata that you can send with every measurement that will be taken for your system. One very common scenario for using tags is enriching the metrics that you collect with metadata of instances on which the metrics were collected. So for example, you might collect the CPU utilization from different VMs. So you can send the instance ID of every VM so that essentially when all this information comes together, you can then filter by the instance on which the information was collected. And you can also add some additional tags to the metadata that is sent with every measurement just to fit your scenario. So for example, in our demo, we are going to use environment as additional piece of information that's important, that helps to do filtering. Okay, next thing is measurement. Measurement is taking the measure at a given point in time. It's like a dot on this graph. Okay, next is aggregation. Even though you see like the graph is not just lonely dots, it's a pretty connected graph. But still, there is only finite number of dots that can be plotted on this graph. And every dot represents a given point in time. But what happens if you have multiple measurements that you took in that point in time? So for example, if here every dot represents 1 second, might be that you took 100 measurements during that second. And so the question then becomes, if we send all these measurements all the way to the back end, how do we represent all these 100 measurements in that one point that we can see on the graph? And this is why we have aggregations. Aggregation is a method that the backend uses to aggregate all the measurements that were taken for a given point in time so that we can represent it as one point on the graph. So in this case, we choose sum, but it really depends on the scenario. It could be mean, max, count, or any other aggregation that you might be familiar with from SQL that basically takes a lot of points and then provides one result that represents all of these points. Next thing is view data. View data is basically like all the measurements that were taken over time with all corresponding metadata that these measurements possess. So for example, every point on this graph represents CPU utilization, but when it was sent to the backend of the choice, it was sent with the instance ID, and so all of these things together, they form view data. If you want some similarities, if you're familiar with the SQL world where you have tables and schemas, view data is like a table. It's like the actual rows that you have in your table. And then our next term, which is view, is like a schema. View is a definition of what we want to measure, what we want to capture. So it's all of the measure, tag, and aggregation, and the name for this table together using one term called view. And view data is the actual measurements that were taken for these definitions. OK, so now let's see the demo of how we can create metrics using OpenCensus in C#. OK, so what I'm doing here, first I'm creating a measure. Now, measure in this case, it has its name, description, and the units. But in this case, the unit is 1 because I'm measuring the number of executions. Then I need to define what tags I want to add to every measurement that will be sent over. So in this case, I decided to send environment and the machine. So I just defined 2 keys. And when I will essentially send this data over to the backend, I need to provide the values for these keys. So in this case, I created an object called ITAContext, which maps for every key corresponding value. Okay, now for every measurement, these things are not supposed to change, okay, because it just describes the metadata that is not supposed to change. And so I created this context, which for environment will send test_env, and for machine will send my machine name. Now there is an object called stats recorder. This is like with trace, the object that collects all of the metrics that were collected locally before these metrics were essentially sent to the backend of the choice. Now, similarly to the trace, I need here to create the exporter that will essentially take these measurements that I produced on my service and send them over to the backend of my choice. So in this second demo, I'm going to use Google Stackdriver, but essentially I could replace it just on this line where I create the exporter. I could replace it to, let's say, Prometheus, which is open source metrics collection system, or some other system from other vendors, and it could work equally fine. I don't need to change any other things in my code for this to work. Only the exporter, which is one of the main benefits of using OpenCensus over more proprietary solutions, which holds you to a specific vendor. OK, so I created the Stackdriver exporter, and then I create the view. OK, so like I mentioned earlier, it's like a schema for a table. It's just defining what columns you have in a table in a way. So in this case, it has the name, description. It has the measure that they want to capture metrics for. And this is the aggregation function that I want to use. In this case, I use count because I count the number of invocations. And these are the tags that I want to send with every measurement. Okay, I just describe what will be sent without actually producing the data yet. And essentially, I register this view because with this view, I can send basically multiple metrics which describe different things, and they all get collected on the same machine. In this case, we will send only one metric, but the reason we have this register view is that you can create multiple views and send metrics for these views. Then this is the actual code that we want to instrument with metrics. So like I said earlier, I want to take measurements of how many times the method was invoked and send this as a metric to Stackdriver. So the method is foo, and in this case, I'm trying to record the invocation of the method. So for the stats recorder, I call the method new measure map, and I put for the metric called number of invocation that we defined earlier, I put its value, which is 1 in this case, and I add the metadata, the tags that we defined earlier with the corresponding values. So this is essentially what will send a point of measurement all the way to Stackdriver. Now, this application already runs for a while. I just created dot every time that this method gets executed so that you can visually see that it was executed quite a few times already. And now we'll try to go to Stackdriver and see what you can get by sending the metrics over there. Okay, so this is Stackdriver, and I'm going to go to Metrics Explorer, which is where all the metrics will go, and this is where I can produce nice graphs on the fly. And I need to find the metric that I created, so it's here in the list of all the metrics. A lot of metrics that you can see here, these are the standard metrics that you get out of the box. If you deploy your code into Google Cloud, you will get a lot of these metrics, mainly for infrastructure, for free. So you don't need to do anything to get them. But in our case, we instrument our own code. So we need to find the metric that we created, which is called sample execution count. And you can see here, indeed, the graph is getting created. You see that this graph is being refreshed with interval of 1 minute, and this is why you see that it started at some point when I started to execute my application. And this is the main reason why I wanted to invoke my second demo ahead of actually showing it to you, so that we can see that we actually have some data that was produced because this foo method was called, and so we recorded the invocation for the metric of sample execution count here. All right, so let's stop it. And similarly, we are going to start the third demo, because it also needs some warm-up time. Okay, so far we saw 2 demos of how you can get started with traces, how you can get started with metrics. Now let's talk about some of the more advanced topics of telemetry collection. So recently we introduced a component called OpenCensus service, which is agent and collector for metrics and traces. Now, one of the problems that we discovered when we started to work on this OpenCensus set of libraries is that sometimes developers want to export the telemetry that their systems produce into more than one backend of the choice. Okay, it could be relevant for scenarios when you migrate from one cloud to another, or it could be because for some compliance reasons you need to store data in multiple places, or there are multiple cases that might be relevant. So with the previous approach of using in-process collection of the metrics and traces, if you wanted to export the data to a different destination, you had to restart the process with the new set of changes that configure the code to export data to a different backend of the choice, which is not very convenient, especially when you run your systems in production. You don't want downtime because of that. And especially you don't want to redeploy your service with new changes for that. So this was one of the reasons why we came up with this OpenCensus service, which essentially allows you to do this. All of the telemetry that gets collected on your machine then essentially gets taken by an OpenCensus agent and sent over to OpenCensus collector, which is configured separately to your code. So if you want to change the configuration of where this information is going to be exported, it could be the same place, it could be a different place. You can easily do that by just changing some YAML file where you can define multiple destinations without restarting your own service. So that was one of the reasons. And also it allows us to do what we call smart sampling. So let's talk about that problem in more depth. So when you collect telemetry for your distributed systems, there are two problems that typically people complain about. One is higher operational costs, and second is noise. So if you think about a system that has a lot of user traffic, majority of activities that you might get from this system as a result of user transactions, they will work. And so the traces that get generated might not always be useful for you, but you will pay for that, right? Because all the traces that you essentially need to store, you need to pay to that backend that you decide to work with for the storage. So it might be expensive. And second, because your system might generate so many trace points, it might be hard for you to really nail this down to what really is meaningful for you. So it might produce a lot of noise, which you obviously want to eliminate. So the solution that we came up with called smart sampling. Now, with smart sampling, you have the power to decide whether you want to take all the samples that were created on that machine or only a subset of them. And there are two types of decision that you can make. First is called head-based sampling, and second is called tail-based sampling. With the head-based sampling, when the transaction to your system comes in, there is this sampler component that decides whether to instrument that trace or not. This decision is taken at the start, so you can say, let's instrument maybe like 20% of all of the traces that potentially can be generated on the system. And so you, this way, can easily reduce the number of data that was produced by telemetry. So it's better than nothing, but it still might be a bit problematic, because what if the incoming request comes in, then your component decides not to trace it, but if that request goes into downstream components, somewhere downstream there will be an error that you don't want to miss. But the decision is already taken, so you will miss that trace. Obviously, we want to have much more freedom to decide what to do with the traces, and to be able to make a thoughtful decision, we need to look at the entire picture. So we need this transaction to end, to see all of these spans that were created as part of this entire trace. If there are errors in the spans, then might be useful to add this trace and send it over to the backend of the choice. For the ones that always produce 200, which is always healthy, might be worth to drop it to reduce the cost. So we'll see a demo of tail-based sampling. And before we actually see the end result of the demo, let's talk about the architecture of what we try to do here. So there is an application that we created at Google for demo purposes called Hipster Shop. There is a link that you can get to the repo and see it. It's an e-commerce application, which you have front end, you have checkout, you have cart service, and so on, just typical application. And in this case, there is a microservice called checkout, which will start running some synthetic traffic through this checkout service, such that in some cases, it will fail the checkout transaction, and in some cases, checkout transaction will succeed. What we want to see is the difference between the tail-based sampling and head-based sampling. So what we are going to do is on the right-hand side. We are going to send synthetic load, and it's going to be sent into collectors. So basically, we create the traces and spans, corresponding spans for these traces that include activities which sometimes succeed and sometimes fail. And then we configure the collector, which is part of this OpenCensus service, to send the telemetry to two backends of choice. One is Jaeger 1, one is Jaeger 2. So Jaeger is another open source system that you can use for tracing. It was created by Uber and got very popular nowadays. You can use it for free. It's all on GitHub. So we'll use two Jaeger instances. One Jaeger instance is configured with head-based sampling, which means that there is some random percentage of requests that we'll trace blindly without knowing how they continue in the downstream systems. And the second instance of Jaeger will use tail-based sampling, where we'll trace only the activities which has at least one error in them. So there is at least one span which resulted in error. And then we'll see the results. So I'm already running this for quite some time. And so we can go into two instances. Again, this sample is running in containers, so it's all running on my machine, but you can also run it in distributed systems. So this is the checkout service. And if I look at the traces, okay, there are many traces that we generated. Like here, there is one trace with 9 spans, another trace, and so on. And if you look, okay, I'm skimming pretty fast, but you can see, for example, here, this is the activity that happened to be without errors, and the next one happened to be with 3 errors. So here we have a mix of activities, some of the traces with failures, some of the traces with successes. A lot of data that we need to digest to see what's important and what's not. So let's go into the second instance. So this is the instance where we use the smart sampling. And in here, you see that every single trace has errors in them. Okay, so this is much more efficient in terms of giving me only the information that I really care about, so I don't overpay for things that I don't need. Okay, so some other things that OpenCensus provides, for example, the zPages. zPages is a term that originates at Google, and this is a hosted service that lives alongside your application and provides visibility into the traces that were generated on that specific instance, be it with traces that you generated as a result of HTTP calls, like you use maybe REST components in your system, or be it RPC calls if you use gRPC. We provide these two hosted sub-services, which are part of the OpenCensus libraries that you can use. And then if you go into corresponding trace Z or RPC Z, depends on what type of remote procedure call framework you use, you can get visibility into what happened on that specific machine. So it's like Zipkin and Jaeger in a way, but only for that specific machine. So in cases when your machine might lose connectivity to the backend of your choice for a reason, you can still see what's going on there. Okay, and it's coming out of the box. Now, OpenCensus provides support for a wide variety of exporters for many existing vendors of observability. This is the partial table, which tells you which exporter are supported for which language, and also for traces versus stats, which is metrics. Okay, this table gets updated quite often to add more and more, and the goal, of course, is to make it full with all the supported systems. OpenCensus also comes with a lot of integrations. So if you use Redis cache, or you're hosted on Google Cloud, or you might use MySQL or some, MongoDB or some other components in your system, you might want to get visibility into what these components are doing, how long every activity in these components takes, so that you can spot bottlenecks, or you can understand better what's going on in your systems. And so these integrations exist for a lot of these external systems. All you need to do is just enable them, okay, which is like one API away. But you don't need to actually instrument every single code to, let's say, Redis, because it's already pre-instrumented for you. And we work on adding more and more integration points so that you can get more visibility into any component that you want. OpenCensus community is pretty active. We have a website, we have a GitHub channel, we have repos for every language, we have Twitter and meetings every month. The last meeting happened yesterday, and it typically happens every month where we discuss the way forward. And there is a slide that was kind of omitted here, but basically one thing that's going to happen very soon is there is another community called Open Tracing, which had similar goals in a way, but only focusing on the tracing in distributed systems. In OpenCensus, we cover both tracing and metrics collection. And so these two communities shared a lot of similarities, and we decided to unite. And there's going to be an announcement at KubeCon in Barcelona about the new name. But essentially, the roadmap of OpenCensus and Open Tracing is to merge, to have the single set of APIs that you can use for your distributed systems to get visibility into your components as well as all potential third-party components that you might use. And so you don't need to choose between the two. Now there is no two, there is only one. The name is going to be shared later on, but you're welcome to join. The development still continues. We are going to work on the merge. The plans for the merge were announced on a Medium page of Open Tracing. We plan to wrap the merge by November, and from November on, you will have only one set of libraries and APIs to use for observability in distributed systems. Okay, with that, I'd like to finish and welcome any questions that you might have. Around log aggregation. Okay, great question. So yes, log aggregation is a very common problem that like everyone who is involved in OpenCensus community is thinking about. Many developers that try to use OpenCensus, they basically gave that feedback that one of the key signals for observability is logs, and so we want to aggregate logs as well. And OpenCensus already came up with the proposal. It was early proposal, it's still in the works, about how we can standardize on logs collection. There are so many different frameworks on logs collection out there for different languages and different scenarios. And this is why this problem will take some time to solve, but it's definitely on the roadmap and it's already in discussion. So yeah, it will happen. More questions? Yeah, so I'm from Google, so obviously I can speak for Stackdriver, and I'm also involved with development of Stackdriver. Basically, Stackdriver is a Google solution for application performance monitoring. So what you get there is all different signals in one place on one timeline. So for example, you can instrument your application with traces, with logs, with metrics. It all will flow into the same system and will show you dashboards that you can customize any way you want. And in that dashboard, you can see all your microservices and topology graph of what microservice calls what microservice, what's the call rate. You can see all the logs for every component, and so on and so on. So yeah, Google provides this out of the box. One of the cool things that Stackdriver has that not every other vendor out there can offer is debuggability. So if you have your application up and running in the cloud, one of the problems that you might experience is there is a bug that happens in production, but they can't reproduce this bug locally, right? Happens to a lot of us. And so with Stackdriver, we have the Stackdriver debugger, which is free for people who use Stackdriver. And basically what it allows you to do is put a snap point on the code which is running in production. And then when that code is being hit, we'll create a snapshot of the memory in that point in time and let you debug into that snapshot without stopping your code. So there is no penalty for your code in production, but you will get a lot of insights into what actually happens in the code of your application. And we support all the major programming languages with Stackdriver debugger. You can also even inject log points, which is basically adding log statements into your code without deploying and also without changing your application, which sounds like too good to be true when you hear it for the first time, but it actually works. So yeah, there are solutions out there that provide you this holistic view of logs, metrics, profile information, debugging, and all on the same timeline. It's just a matter of you choosing what works best for your use case. And with OpenCensus, it's still valuable because you might be in the scenario where some of your components run on different clouds or maybe on premises, and you want to have this holistic view of everything, not just components that run on specific cloud provider, but for every component in your system. And with OpenCensus, you can do it. And even if essentially you take your workload, let's say, from on-premises into the cloud, still you will not need to change almost anything in terms of observability, maybe just the exporter, which is like one line of code. And then all the rest of the APIs for metrics and traces collections will stay the same. And suddenly you get the same visibility of what's going on, but now your service is already running in the cloud. So it's really powerful. All right? Yeah. Yeah, so you mean messaging systems when you can like broadcast the message to multiple components? Yeah. So for the Microsoft messaging systems like Service Bus, I don't think there is existing integration that you can use today, but it's definitely on the roadmap. Yeah, we work with Microsoft on this OpenCensus set of libraries. Microsoft is a very active contributor alongside Google, alongside Dynatrace, and some other folks out there. And so, yeah, it's definitely on the roadmap to make sure that you can get visibility into all the components. All right, so thank you very much.